So, once again, good morning. My name is Peter Arras. I come from the University of Leuven in Belgium. Belgium is a small country, 20 times smaller than Ukraine. Our university was founded in 1425, so about 600 years ago. We're one of the oldest universities in Europe. And this morning I'm going to talk to you about 3D additive manufacturing, which is a name for a lot of stuff, as you will see. If you have questions, please ask. Don't wait until the end, but if you can ask questions intermediately. Okay, so what is additive manufacturing? Essentially, well, it's a name which is used to tell a lot of stories. The old names for this was rapid prototyping. This was more or less the first name which was invented for this. But layer-based manufacturing, digital fabrication, solid freeform fabrication, rapid manufacturing, 3D printing, which is now a very popular name for some technologies, is used. But in the end, it's all comes together, and we call it additive manufacturing, because from the nature in these technologies, we build up parts by adding material instead of using subtractive technologies like you have in the past, like milling, drilling, and so on. There you take away material. So we add material. Okay, so if we look a little bit at a definition, so it's called the process of joining materials to make objects from a 3D model data, and usually it's done layer upon layer as opposed to subtractive manufacturing technologies. This is a definition, an American definition from the standards, from American standards. Yeah? It's got a lot of advantages. It's flexible. You can do a lot of customization. You can do it locally. We'll see. You can use new materials which was or not so good available before. And it's an ever-increasing market. Yeah? Long time ago it started. 3D printer costed very much. Nowadays you can buy a 3D printer in the shop for a couple of hundreds of euros and print something at home. So it's become more popular, of course, and so the number of 3D printers which use some of these technologies has risen, of course, during the years. Okay, if we look a little bit at the two things, what's the advantage from subtractive manufacturing and additive manufacturing? Subtractive manufacturing is the things which we do with chipping. You take away material and then you end up with the shape. And in additive manufacturing, we add material in one way or another and we build up a complete part. So that's the two differences. Let's say the two technologies. Now, what's the advantage in the one or the other? As subtractive manufacturing, material cost is low. If you buy raw iron, steel, it will cost you, I use euros because I come from Belgium, like 1 to 2 euros for a kilogram for ordinary steel. If you buy material for 3D printing technologies, you start from something like 100 euros for a kilogram, going to thousands of euros for a kilogram. And then I don't mean that you will be printing gold, but you will be printing metals or something, and then you get to a cost of thousands of euros for 1 kilogram. So material cost is for sure an advantage of subtractive manufacturing. Yeah? On the other hand, if we look at complexity of your part. If you have a complex part and you need to make this with subtractive technologies, you will spend a lot of time machining and you need a lot of tools. So for the tooling side, subtractive manufacturing is expensive. From the point of view of additive manufacturing, complexity is free. It doesn't matter if you have a complex part or a simple part, cost will be the same. So you can get to much more complex parts with a cheaper manner. Okay, so if we then see for the slogan, let's say, subtractive manufacturing, we design for manufacturing. You make your design so that you can try to manufacture it as easily as possible to get to production. In additive manufacture, we manufacture for our design. You make a design, doesn't matter how it looks like, you can 3D print it with one or another technology to come to a part. Of course, there is some other things which we have to take care of into consideration, as we will see a little bit later. Now, how does additive manufacturing work? Well, it's pretty essential that you start from a 3D model data. Yeah? You need these data. Without 3D model data, you will never get something 3D printed. So that's one thing you need to start from. But further on, there is this one of the things they say, you don't need knowledge to make a part with 3D printing. Well, I must say this is not true. You need to think a lot about strategies, about things to produce your part. If not, you end up with a shitty part with no quality. So you also need knowledge, but different knowledge from subtractive manufacturing. So 3D data can come from a CAD system, which is mostly used, or from 3D scanning part which you made. Then you make an STL file. We will look at it, how it looks like. STL file will convert your 3D data in kind of format which the printer or the software for the printer can use. Then you start up slicing. You make all little layers in your part. You print them, and then you finish your part, because the part has got not such a good quality at the end, so you mostly need some post-processing or printing. So if you look at it, this is essentially what's happened. So layer by layer, you build your part, yeah, with one or another technique. So we need a digital file. Then we slice up the file. Means we will cut the part each time in little slices. And when you print these slices, you end up with your part. Yeah? That's the main idea. Okay, so the first thing is slicing. And if you slice something, if you slice an STL file, you end up with just this contour, the outside of your part. The inside of your part is gone because it's not represented in the STL format, as we will see. So you only have the outside of your part for each slice. Yeah? So, okay, this one you can print. Next, you need to think about a strategy to fill your part. Because a hollow part, you end up with like chocolate figurines, like for Easter eggs or something. Yeah, this is not very good part, hollow part, because they have no strength, there is nothing in it. So you also need a strategy to fill up the interior of the part. Okay, so this is already something to think about, of course, how you get to the outside and what to do with the inside of your layers. So this is mostly called hatching, some kind of hatching you will use for filling the slice. Yeah? And depending on the technology which you use for 3D, so for additive manufacturing, this can be very important to have a good look at it, because it will determine the strength of your part, how you make the inside, as we will see when we talk about materials and so on. Okay, so you have to make the outside on each layer, one or more layers from the outside you will be making, and then the inside you will be cross-hatching it in one or another strategy to do so. So the thing to start from is the digital start file. You make something in your CAD system, and then you convert it to a STL file, which stands for Standard Triangulation Language, or Triangular Language. It gives you, what will it do? It will convert the outside of your part and will put little facets on it, all triangular facets. Because with triangles, you can fill up every shape. If you look at the circle, and you put in circles, you try to put squares in a circle, you will not end up with a circle. You will have something with a lot of corners. If you use triangles, you can get much closer to your shape. Now, it's a pity that I don't have much of the blackboard left, but I will. Here is a little bit of a part. Ooh, you see this? Okay, if I put a triangle here, I still have this, so I cannot make my perfect shape. Yeah? In this STL file, you lose a lot of the description of your geometry, and you end up with a very, let's say, coarse approximation of your part. So from the point of view of what's called resolution or accuracy, we have a problem there. Yeah? Also, we lose the mathematical representation. This means if you look at this sphere, you don't end up with a sphere, but you will end up with something with corners. Yeah? And nowhere in the file you can find that it was a sphere. You only have triangles left, which is from the point of view of manufacturing not very good because your accuracy will disappear. Okay, and then your part will look like this or like this. But now you say, okay, but this is little squares. No, a square is two triangles put together. So.
I'm sorry.
Yes?
Why people don't use spline?
This comes from history. 3D, this technology was, we will come to history a little bit later, and then I'll explain. Yeah? And then you will understand why it's like this. Okay. Let's quickly. Yeah. Just wanted to show this. In the 1960s, they first tried to do this. They thought about a way of starting 3D printing. Well, at that time, computers was scarce, very expensive, and not powerful. So you need a mathematical description which doesn't take too much space in your computer. And then you can't use curves. Then you should use something simple. And what is simple? Lines. Lines is very simple mathematical thing. The equation of a straight line is easy. So in the STL, STL is described as each of these facets is a triangle. Triangle consists of 3 corner points. Yeah? You put them together, so this is the vertices. Yeah? They make a loop counterclockwise, and what we also describe is a vector, the normal vector to this facet, because this vector will give the outside of your part. So you only end up with the outside of your part, and the vectors show where the material is. And now it's very easy. If you now want to find out where you need to print, then you have all the little layers which will be here, check, 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 check. And essentially what are you looking for? The intersection of a plane with a constant z coordinate and a line between 2 of these facets. Intersection of a plane and a line, this is more or less basic mathematics. Everybody can do this. Yeah? That's the reason why they use this STL format. It was so easy from the mathematical point of view. You don't need a lot of computing power to find out where your printer needs to print. Yeah? Okay, so it comes from history, but the problem now, of course, is nowadays we would like the mathematical description. But it isn't changed anymore because everybody uses this format. Okay, ask your question.
Yeah, I'm sorry, but you said that it was voicing when it was 60, everyone listened to the Beatles, and the computers weren't so powerful. But nowadays we have like 2017, so our computer is still so weak we can't use
Yeah. That's true. but changing something is very tough.
So it's kind
So
of,
people don't want to change it anymore.
okay. That's pretty much it.
That's the only thing. Yeah?
Do we use the same like a system in nowadays though?
Sorry?
Do we use this like the same system?
If you do 3D printing, if you use 3D printing technology, it's all using this description. All. So you end up with stupid parts, of course, because you lose all the geometry. You don't have anything left from your CAD system, only the outside. Yeah? You can't change it anymore. It's plain stupid, but that's how it works. There is some other things which never change, like for instance, if you buy a CNC machine, computer numerical controlled milling machine or drilling machine, if you look in the data sheets, you will find that the memory is also expressed not only in megabytes, but also in meters tape. Because in earlier days, they used a punched tape to put in the data in a CNC controller. And you will still find in the data sheets how many meters of tape you can put in the machine. So memory expressed in meters instead of megabytes. This is also from historical reasons. Yeah? What has improved is nowadays you can use floating point data, so you get somewhat more accuracy in there, because in early stages you only had integer numbers there, so you should cut up your part in integer numbers. And also you could only use positive quadrant in the past. Nowadays it doesn't really matter anymore. So there is some advancement, but not much. So STL format, because of the simplicity. There was another format also available, CLI. Yeah? No, from the STL they use code to go to the machine, sorry. So the most used code nowadays is G code, just like CNC machining. It's the same codes, G1, G0, and so on. So these controllers are based on the same controllers as the CNC machines. And a CLI file also existed. We will see layered, common layered information. And it's a pity. So you will see it gives some advantages. So G code is readable, looks like this. Yeah? We only use, if you know something about machining, but we only use G0 and G1. You only have linear stretches. Yeah? And you only do printing, G1, or not printing, G0. That's it. So it's not very complicated. There is some other parameters which you use. SFMM parameters, the scan speed, extrusion speed, and temperature settings. Scan speed is the speed at which your printing head device moves over your part. This is the scan speed. The extrusion speed is the rate of material that you add. And the temperature settings is the temperature settings of the printing head in the technology. And this all has to do with quality. Yeah? Especially if you print plastics and so on, it's very important to have a look at temperature settings for a good solution. So a file driving your printer will look like this. That's all. Yeah? It's very simple. The other format was common layer interface. Yeah? This gave possibilities for, you see here, polylines, hatches. Yeah? It offered more possibilities, but this is not used anymore. Why? Because it tends to be a little bit more complicated for the people who build 3D printers. Yeah? If I want to sell a 3D printer to somebody for use at home, it needs to be cheap and easy. So I use a cheap and easy way of programming it too. And this is not cheap and easy if you use this. But this gives gave better possibilities. Okay. But so this nearly disappeared. So if you look at history, first attempts were made in the 1960s, which you can see if you look in science fiction movies of these days. You will find traces of 3D printing things that they thought about doing. But it was only, the late 1970s, the first patents were made, and the first machine which commercially was available was 1987. So it's nearly 25 years after the first idea about this technology that it was available. Okay, this is already some time ago, 30 years ago. 30 years ago they said, this technology is it. Within 10 years it will substitute every other way of manufacturing. Yeah? If you now open a magazine on 3D printing, they say within 10 years this technology will substitute every other way of manufacturing. And I'm sure in 20 years you will read in the magazines, this technology in 10 years will substitute every other way of manufacturing. Yeah? Why? Because it looks nice, it is nice for some things, but it's got a lot of disadvantages if we look at real production, as we will see. Okay, 1991, the first commercially available fuse deposit modeling machine was available. This is the technology which you use if you buy a cheap 3D printer for use at home. Yeah? So we will come to it. 1992, introduction of selective laser sintering. You see, and at this time, there was a big speed up in technology. And this mostly has to do with the fact that computing power became cheap. In the 1980s, all of a sudden computers were available to everybody. Because before it was too expensive. In the 1980s, you could buy already personal computer for, okay, a couple of thousands of euros, which was 10 times less than 5 years before. So at that time, computer power was available, means a lot of people started to use this, evolve on this, and they made these new technologies. Okay. It goes further, some other technologies, we will come to it. The latest technologies which is available, aerosol printing, this special technology as we will see, and from, let's say, the last 10 years approximately, these two technologies arose, and they are very promising for some special things, and the last one for sure, with welding equipment, build up materials with welding equipment, will have a nice future. Yeah?
This for metal?
Yeah, this is for metal, mostly. With aerosol printing, you can print anything, going from metal to plastics to even biomaterials. So if you want to print a hamburger, you use aerosol printing. That's exactly it. But we will come to some of these technologies a little bit further when I discuss them. Okay, now if we look at 3D printing or additive manufacturing techniques, there is a lot of things which you have to take in consideration. There is things like accuracy. How accurate you want your part to be. We have this here. We have a problem with accuracy. We know. You cannot make the perfect shape. But how close would you like to get to the perfect shape? If you use metals and you use a milling machine, then you can get very close to the theoretical or the perfect part. In metal, you can go like in the range of a couple of microns close to your perfect part.
For microscheme, for example?
From? For?
Microscheme, for example?
No, but just with milling and turning machines and so on, you can come close in a couple of microns to your perfect part. With 3D printing technology, we speak close, now we say something like maybe 50 microns. This is not very close. This is very inaccurate. Yeah? So accuracy is a big thing. Yeah? Other things which is interesting to look at, which kind of materials do you want? Yeah? We are here in a foundry department, or there's a lot of things against the walls on foundry. If you want to use metals, you need other printing techniques than if you want to use plastics. But if you want a functional part, yeah, plastic printed car will not be very good. Yeah? So this in consideration, what kind of material you want. Cost is a very big issue. I told you about the cost. If you manufacture something in steel, like these benches, 1.5 euros for a kilogram. If you 3D print it in metal, 5,000 euros for a kilogram. So you have to take in consideration how much you want to spend on a part. Build size. How big you want something to be printed. You have nice techniques like aerosol printing. You can print in the range something like 5 microns accuracy. But the maximum part that you can print is something like 5 to 5 to 5 centimeters. That's very small. So if you want to print these benches, for instance, then you need a very big printing machine with a technology which allows to do this. Yeah? So build size is a limitation. Mechanical properties which go together with your material, of course. Resolution and accuracy. It's a little bit different. Accuracy is how close you come to the perfect shape. Resolution has to do with how thick is the layering. Yeah? So it's two different things. Speed. How fast does it need to go? Yeah? And support structures, as we will see. There's some problem. Like support is this. If you 3D print something and you use a technology, this is the material which is printed, but any material is influenced by gravity. Yeah? So if you print something and there is nothing underneath, your material will just fall. Yeah? You don't want this because then you have something ugly. So you need to put on supportive materials, yeah, for doing this. Okay, this is important to know. Like most 3D printers you buy to use in your kitchen, at home, for hobby, they only have one printing head. So no support structure. So you have a problem there. So you need to think about another strategy. So this is support structure. Some technologies it's necessary, in other ones it's not necessary. So support the structure for this. If you want to print this cup, you print from the bottom up, but once you come here, where you hold the cup, this will fall. So you need to print supportive structure. So this is the supportive structure which is printed underneath. Okay? This is nice, and this is what I get. So I need to take out the supportive structure. If it's in special materials like this one, which you can use, so you can print in ABS, for instance, or other of PLA or whatever, PVA. These are some materials you use for 3D printing. And then the support structure in another thing. These support structures, you can dilute them with acids. So you put your cup in like lemon acid or something, the support structure will disappear. Yeah?
Different materials.
Yes, it's different materials. But then you have, of course, some chemical pollution. It's not so clean. You have some kind of a container with lemon acid in it and these diluted plastics. So what's next? Everybody throw it down the gutter. It's not a very good idea because you pollute environment. It's not. If you cannot print it in a different material and you use the same material, then you should afterwards drill and mill and whatever to get the support of. Yeah? So something to think about in your technology.
I'm sorry.
Yes?
So as far as I understood this, the 3D printing is expensive, non-accurate, and we cannot get something bigger than, we can get something really big. So is there any, can you name a real purpose for 3D
Yeah.
printing?
Prototyping.
You cannot spend millions of gold.
To make prototypes is very useful.
Prototypes of what?
Of anything. To look at, to see how it is, to see how it fits, and that's it. But for making functional parts, it's not really good. In some niche markets it is, as we will see. For instance, in medicine. Yeah? You go out, you fall from the stairs, you break your leg in 10 places or something. Yeah? It needs to be put together or they need to substitute because part of your bone is gone. You never know. Yeah? Well, for this, You 3D print part of your bone, put it in, very good, don't need very accurate technology, and also in medicine, cost is no issue, what you know. Right? For implants,
If you have medical coverage.
yeah, but it's the same. It doesn't matter. In medicine, cost is no issue. That's essential. If you don't have insurance, you cannot afford it.
Probably in Belgium, yes, but in Ukraine, yeah.
No, it's the same. In Belgium, it's also expensive, but that's just it. Cost is no issue.
You've never had experience with Ukrainian medicine, okay?
No, but you don't understand what I'm telling you.
No,
In
no,
this-
I got you.
In this niche market, medicine, cost is no issue. So you can 3D print something because people will pay for it anyhow. Yeah? Another thing in the world where cost is no issue is like spacecrafts and planes. Yeah? Cost is no issue. That's why launching a small satellite 10 by 10 by 10 centimeters will cost you in the end 1 million euros when you develop it and launch it. So their cost is no issue, meaning if you 3D print something and it will cost 1,000 euros for a small part, that's okay, because it's only a fraction of your total cost. And that's the same in a niche market like medicine. Yeah? It's not really an issue that it's costly there. Okay, but we will see. So we can classify technologies. Most interesting classification is what can you print? If you want to print plastics, you have a lot of technologies available. If you want to use metals as a base material, there is not so much left. If you want to do ceramics, there is even less materials left, or technologies left. And if you look at it, why is this? Because plastics don't demand a lot of energy. A plastic will melt at 150 degrees, 200 degrees. Plastic will melt. Yeah? While metals, you're a metal department, material science department. If you want to melt steel, you need kind of a high temperature. Yeah? And for ceramics, it's even worse. Yeah? So, of course, high energy technologies, there is not so many around. Yeah? Low energy technologies is easy to think about, maybe a new technique or something. So that's the distribution.
And what about the properties, stresses, for example?
Now, I'll come to this later.
Oh, okay.
I want to try to keep some sequence in my presentation. Okay, according to American standards, there is they let's say substitute it or they catalog it. With photopolymerization of liquids. This is like stereolithography. This is the oldest technology. Material jetting, where you use droplets of material. And this is not only plastics, but you can also use droplets of concrete, for instance. You can 3D print concrete. Binder jetting, where you use kind of a glue to put things together, as we will see. Material extrusion, these plastic printers which you can buy for some euros. This is all fused deposit modeling, material extrusion. Sheet lamination, it's also important, and this is also especially important for what I see here against the wall, for making castings, as we will see. Powder bed fusion, this is very important for metal parts. Direct energy deposition, yeah, also. Okay, so we quickly go through some of these technologies to describe and then come to some important things to think about when you make parts. So the first, oldest technology was stereolithography. It's still used very much. It works with, you have a fluid polymer. You know polymer, plastic?
Yes.
Huh? So we have a fluid plastic. Here you have a tray, yeah? And then here is a light source. Either UV light or laser light can be used. And then you harden this liquid plastic. Yeah? When a layer is hardened, the tray goes down, you harden out the next layer, tray goes down, you harden out the next layer, and so on. In the end, you have one part. Yeah? what its advantage in this? Well, it's a liquid. A liquid means liquid is uncompressible. Yeah? So you don't need much support structures because the liquid will keep your structure. You only need a little bit, especially if you have long overhanging parts. So that's very advantage. Also, with stereolithography, you can use big parts. You can print big parts. Like this part, which looks like an animal, but it isn't. This is the dashboard of Ford Mondeo. If you know a car, Ford Mondeo, if you look at the dashboard, it's pretty big. This is size something like 1.5 meters, and in this direction maybe 80 centimeters. So this is a big part which you can print on a big printer, of course. Yeah? So you can use big parts, and you also have quite fine layering. So the layers, the resolution is quite okay in SLA. Yeah? In this was used 2,700 layers. It's quite a lot. And the building time was 52 hours. So considering speed, it's quite okay, because if you have to make this with another technology, you will spend more than 52 hours. Yeah? But it's not a functional part. It's only to see, will it fit in the car? How does it look like? So if people think this is okay, because you can look at your CAD design on the screen, but it's still very different if you touch it and if you're able to look at it from all sides and so on. Okay, so stereolithography, nice technology. It's the oldest technology around for 3D printing. Fused deposit modeling. This is the most common one, especially what you see as consumer, because this is the printers you can buy for use at home. Yeah? It works with thermoplastic polymers, filament or extruded, and you make all of these little sausages of plastic, put them together. Yeah? So you need to get the plastic here. Plastic can come from a wire which you melt, and then by melting it, it will stick to the previous layer, or you can extrude it, starting from granulates, and then you extrude it at the spot. But the effect is the same, so you have a sausage of thermoplastic polymer coming out, sticking together with the next ones. As we see here, you have a big problem with accuracy and layering. Your layer can only be as thin as your wire is. And then, sorry?
Centimeters or millimeters?
There's millimeters. Yeah? So layering thickness in this case can go somewhere to 0.15 millimeters, because of course you get a little bit less thickness than the wire because you melt your plastic. Okay, but you have problem with accuracy. If you look on the top, you have these little waves of wires. So there is no surface finish. There is no geometrical accuracy there. There is also a problem with the material and the strength, because you need to do this by heat. Yeah? So if I print a long stretch and return, my plastic here is very cold, so the next layer will not stick very well. So you have the problem of adhesion between layers. Okay. It's not only plastics which is printed, also concrete, chocolate, for instance, as a biomaterial you can print with this kind of technology. Yeah? And essentially WAM, so wire, arc welded thing is also according to this principle. Yeah? Most common materials used here is PLA, polylactic acid. That's something which you can use at home. Also ABS, acrylonitrile styrene, is a very popular plastic, but you have to see there is also some dangers in it. If you print ABS at home, it's not very healthy, because in ABS there is styrene. You know styrene? This is one of the products which cause cancer. So if you melt your ABS, the styrene will get into the air. So it's not a good idea to go to a 3D printer and smell what he's doing. Huh? This is very unhealthy. So if you print ABS, you for sure need to do it in a ventilated room. So there is some dangers in it. There is other plastics, also PVA, which is also popular plastic, which is used, but it's got also some kind of problems. PVA is also used for hobbyists. Yeah? The big thing is PVA is a very hydrophile, means it takes water from the air. If you leave the wire on the machine and you don't print for the weekend and you return after the weekend, your wire will be gone. It will take so much water from the air that it will just stick together or fall apart. Yeah? So there is some problems in materials. The same with ABS is also kind of hydrophile. It also takes water from the air. And so your accuracy is also gone. Okay. With this technology, with plastics, let's say you reach kind of a layer thickness of 0.15 millimeters, approximately. This is an example for printing with concrete. This is the same technology, but concrete printed. So you have a double print head. One prints concrete, the other puts a steel wire in here as a reinforcement. Yeah? This is printed for a bridge. This is the bridge. It's a bridge in the Netherlands. It's about 8 meters wide. So all of these segments, so this direction is this direction. Yeah? This looks nice, but if you think about it from the point of view of material point, concrete has a very good resistance to pressure, but no resistance to tensile forces. So this means these layers, they break apart like shit if you put some tension on it. So probably in these holes, which you don't see here anymore, there is steel reinforcements or something. So it's more like ornamental concrete than really functional concrete, which is done here. Okay, in China they print complete houses. A house is pretty simple because it's yeah, like putting Lego blocks together, but it's very easy because there is no tensile problems, tensile forces in a house. Okay, but you can do this. Now, one of the big problems with FDM, all of these things, is the supporting structure. If you want to print something and underneath is a hollow thing, you need to print something, either in supportive material, which you can dilute in this kind of containers, or either you use the base material and then at the end you have to take it out, which is not always easy. So the bottom part, the bottom of your part will always be a little bit damaged if you do this. Yeah? But okay, it's nice. What you also have with FDM, because of this non-accurate part and also the surface roughness, you often need to finish. This is a part before finishing, after finishing. This looks very nice. What happened? You use, like, for instance, acetone. You know this acetone? For nail polish remover, this is acetone. Yeah? This is the same part. This is dipped in the acetone. The outside of your part is gone. This is essentially what happened with this OWL 2. Gives a very smooth surface, but what you take away plastic, so your geometrical accuracy is gone. This is with acetone, with vaporized acetone. You can do this cold or hot, depending on what finish you want. Yeah? This is a technology. Acetone is also not very interesting chemical. It's osmotic, means it goes through your skin into your blood. Yeah? If you use nail polish removal, use kind of cotton thing, don't dip your fingers in it. This is very, very unhealthy. Yeah? You will probably not do this when you use the nail polish removal, but this is what people sometimes do when they use 3D printing parts and they want to finish it. Oh, easy, take it, put it in the acetone. Yeah? Not a very clever idea, I must say. Okay, Other technology, 3D inkjet printing. This is different technology. You use a powder, yeah? So you make a very fine layer of powder, and then you print glue over it. So where you print the glue, like with a normal printer, there the powder sticks together, and then you have, at the end, if you do this layer by layer, a part. This is nice technology. It can be used for, mostly for kind of plastics, but also for like starch. Starch, you know this? It's what you use in the kitchen, made from potatoes or maize to make the sauce a little bit thicker. You know this one? Maizena. No? Some people know this. Nobody cooking. Nobody cooking at home.
No, everybody.
Everybody cooking. So everybody should know this. No? What's nice about this technology is that you can use different colors, because what you print is like an ink, the glue, and you can use different colors. So the outcome is different colors. It gives very fine parts, but not very strong parts, because the strength comes from the glue itself. Yeah? You can also do this with ceramics, metals, but then you need to treat them afterwards, like heat treat them or something, so that they will keep sticking together. But it's not. It's essentially technology used for prototyping too. Aerosol printing. In this you use an aerosol. You know aerosol? It's like deo. So you use a kind of a medium in which you have very fine drops or something. This is the same. So we use a gas, and in the gas we disperse some very thin particles, and these particles can be anything. Yeah? There is different technologies for making the aerosol. That's not so important, but what's important is with this you can get very thin layering, yeah? Very accurate, but very expensive, because you have no speed, no build-up speed. Okay?
Do you know approximately size of the particles?
Yeah.
Okay.
You can get to layer thickness of 25 nanometer. This is the size of the particles.
But this is layer, not
Yeah, but that's
particles.
the thinnest layer is the thickness of the particle.
One particle.
Yeah.
Okay.
So you have very fine particles which can be used here. Yeah.
5 nanometers.
Yeah, that's very fine. Yeah. Okay. And you have fine resolution in this, but the problem is it's very expensive. This is a machine which is in our campus, costed 350,000 euros. And you can print something like 3 to 4 centimeters in each direction, and that's it. You can't get more. So that's very expensive. It's very accurate, but this is still experimental printers. There is no production on this. So inks is silver-based, but you can also see like graphene printing and so on. You see very new materials, yeah, very expensive things. Okay, what it's used for instance, this is, you see the size. Yeah? This is an imprinted sensor for like, this is for smart textiles. So you wear a jacket, inside your jacket is printed sensors which give information, could be about your health, could be whatever you want. So you see here, this is very small item, of course. It's kind of a strain gauge which was printed on the textile. So, and for biomaterials, this is also important. So it's used a lot for these things. Okay, another very important thing, especially if you look at foundry and castings, is laminated object manufacturing. In this technology, we use sheeted material. This can be paper, can be a plastic, can be a composite, or very thin metal foil. Yeah? You cut out the shape with a laser. Yeah? Then you put glue, you put the next layer, you cut out, you put glue, next layer, you cut out. Yeah? And in the end, you have a complete part. This is used for big parts. This is a chair. yeah, made with this object, laminated object thing. And here we see, so in the end your part is finished, but it's hidden inside the rest, so you need to break it out. And then you have these things. This is made in paper, glued together, but then you impregnate with the resin, and this is used as the cores for sand casting. You know this technology, sand casting? Of course. Yeah, I don't know if you're all from the same department. Yeah? So it's against the wall, there is some nice views with cores. So you can easily make these cores with laminated object manufacturing. But then impregnate them, because paper itself is not so strong, but if you impregnate with resin, you have a core which you can use to put in the sand and reuse afterwards. So this technology, and this can generate big parts, really big parts. Yeah? Accuracy, thickness of your layer is confined to the thickness of the base material. So these layers range something like 0.1, 0.15 millimeters. Yeah? And accuracy is, in the other directions, is not so very important. If you want to use this for a casting, your casting is also not very high accuracy, because you have shrinkage and so on, so you have a lot of other things to think about. So, but this is interesting technology to do it. So for your sand casting, okay, make this core with the technology, with the LOM technology, and you're good. Okay. What is also often 3D printed is like for investment casting. You know this one also, I suppose? Yeah. So you, with the wax, and you coat the wax with ceramics or with sand or whatever, and then you cast, wax flows out. But printing the wax part is easy. If you have a very large production, you first make a mold to make the wax parts. If you have a one-shot production, you better 3D print the wax model, and then you already have your investment casting parts for afterwards. So is also technology which is used. Okay, then we have some technologies which give somewhat better accuracies and better parts. Selective laser sintering. You know the sintering process? You put together small parts of material by heat, more or less. This is also what happens here. So we have layers of very thin powder, yeah, and the powder we glue together, let's say, we heat with the laser light, and it melts together. Yeah? Selective laser sintering is done on polymers. Yeah? So mostly, or in the past they also used for a little bit for metals, but it was different. It was like making M&Ms. You take a small ball of metal, put some plastic around it, and melt the plastic together. Yeah? And afterwards, when your big part is finished, you burn out the plastic and infiltrate with bronze.
Because temperature is not high?
Because the temperature is not high, because this technology was started in the 1990s. Once again, the technology part. The lasers at that time had low, very low power. You could only melt plastic together. Yeah? It's still used, it gives, because of accuracy. It gives quite nice parts on the point of view of dimensional stability, and the layering is quite okay. Roughness is not okay. Yeah? Now we do selective laser sintering. It's essentially the same thing. Once again, powder which you stick together with the laser, but now you have high-powered lasers. So now you can use metal powders and ceramic powders, which you immediately melt together. It's not sintering, you don't have to heat-treat it afterwards or burn out something, but now you immediately put your metal parts together. Of course, you need very fine metal parts. And then afterwards, out of the powder bed, inside is your part. You have to clean it, blow off. It's also quite unhealthy, of course, because this powder is very fine dust. Yeah? You have very thin particles which you use. Yeah? But it's a good technology. With this technology, LOM can generate functional parts. Selective laser melting can also generate functional parts, and in this case also with high strength, because you can use metals directly. Yeah? But still there is some things. If you look at this, this is the printing direction. A printed layer is a smooth layer. Yeah? But in between the layers you see these boundaries. And then you know, of course, as a material scientist, the direction of your part will give you a different strength. So your material in the end, your part, is not anymore isotropic, but it's anisotropic materials. The material properties will change depending on the direction. So this means that you need clever strategy to know in which direction to print your part.
And what
Yeah.
about support?
In this, no, you don't need support in selective laser because the powder is there. The powder will support everything else. The same in LOM, you don't need support because the other material which you don't use is there.
But when we melt the metal, the shape will be changed?
Yeah, like any thermal process, you have a problem of shrinkage, which you need to take care of or think about when you design a part. But we will come to it a little bit later. So it means you have the layering. Layering means you have anisotropic material properties afterwards in your part. Yeah? There's a big difference with a casted part and a 3D printed part. In a casted part you have isotropic properties, in 3D printed not. Okay. You can also do this with laser or with electron beam machines to generate enough power. They can also do this. Oh, let's see, return 1. Yeah, I'm messing up a little bit. Okay, there's another technology, wire and arc additive manufacturing, WAM. This is done with welding. Yeah? You see a welding robot build up materials, yeah, just by welding. This is very interesting because any metal you can weld, you can use to do this. Yeah? And then you get parts. And then, of course, these parts afterwards you can, if necessary, finish with milling machine and so on to get accurate dimensions. Yeah? The advantage of doing this is for this kind of structures, like what you see here, this support was welded in 24 hours. Which is quite a long time. But if you have to make this from a solid block of material, yeah, then you spend a lot of more time and you waste a lot of materials. Yeah? And welding is a process which we already know for 150 years approximately. So by now we have a quite good idea about properties of your material and about what you need to do this. So this is a very promising technology for additive manufacturing for the future. It's already done with especially exotic materials, more like titanium alloys and so on. Yeah? Because also these materials, if you want to use them in bulk, it's very costly. Yeah? And then if you have to subtract a lot of material to make a part, it's even more costly. So better like 3D print it with this technology, and then you come much closer to your final part. You need to chip less. So this is somewhat called the build-to-fly ratio. Yeah? If we do this from a solid, on this case, the build-to-fly ratio was 12, huh? Meaning that you have 12 times more material at the start than you have at the end. So you waste a lot. With WAM, you only at 2.3. This is not finished, but the finished part, of course, looks a little bit smoother. So you still take away some materials here, but you have a lot of savings in this case. So the cost is 1/3 of the original one, and the savings on materials and so on, 69%. Yeah? If we would do this with steel instead of titanium, yeah, the build-to-fly ratio is the same, but you see also cost is much less and the savings is bigger. So this is a very promising technique. This technology will, the next years, evolve for sure, and will give good results. Especially not for mass production. For mass production, it's always not a good idea, because in the end you better use castings. But for small, very small series and so on, this technology will for sure evolve. Yeah? Okay, another part, and you will see here the mass. So because if you want to make something like this is from turbines, yeah? You know, if you want to make it from a solid block, you spend a lot of money in it. Yeah? Okay. So if you look at metal parts, we have selective laser melting as a part. This is powder-based. Powder-based things is you can make very fine things with it. You see here, and here you see an application of medicine implants. Yeah? Part of the skull which is replaced and so on for people. You can customize it easily. First 3D scan somebody's head, and then you know what to make to put in if there was an accident. And this is scaffolds. This is also used medical. Implants in bones. This is hollow structures in titanium, because your material needs to be biocompatible, and hollow, so that a new bone can grow in there and that you get strong thing. This is something which traditional technology you cannot make. Look at the size of what's next to it, this little coin. You see this is very small. These holes is in the range of millimeter and sub-millimeter dimensions. So to make a scaffold, a hollow shape like this, of course, this is difficult to make with traditional technologies. For this, powder technologies is okay. For big parts in metal, you can also use powder technology, or this one. This is an example of a finished part then. Bigger parts which you can make.
Is it okay for medicines that we have anisotropic properties?
Yeah.
In this case?
Of course. If you have a partly titanium skull, this is much stronger than the rest of your skull. So it doesn't matter if in this direction you can only take 1 ton and in this direction 1.5 tons, because the rest of your skull will be crushed at 250 kilograms. So the anisotropy of your printed part doesn't matter for medicine. Okay. So it's another example, kind of a bucket which was made. If you want to make it traditionally, it would cost you something like half a year to make it. If you do it with this one technology, you can make it in a couple of hours. So this technology, some examples, which is interesting to make because, of course, you will not arc weld up anything. You do this for special structures which you cannot make, or for one part things, which is complicated. Yeah? But you can make it then with very interesting interiors and so on, which are in other ways of doing is often very difficult, also in casting. So, and you can also weld together different materials. You can weld like aluminium to steel if you do it correctly. Yeah? And if you make separate parts, it's rather complicated.
What system we need for
Welding robot, welding machine. That's all. And of course, some clever software thinking. There is companies also in Ukraine who is doing this. Pretty interesting technique. Okay. Yeah, I'll skip this. Another technology for with metal is laser cladding. Laser cladding, essentially, you use powder which you, with laser beam or something, deposit on existing structures. This is often done for maintenance purposes or for repair purposes. Laser cladding. Here's some other examples from metal parts made with selective laser melting, yeah, these kind of scaffolds, but also for castings it can be very interesting for molds. If you want to make a mold for plastic molding, yeah, What's very important in this is cooling of your product. Yeah? You should have cooling channels close to the surface. Well, if you want to make this like in this sphere shape, these cooling channels, with traditional technology, this is complicated. With these selective laser melting, you can print your cooling channels very close to the surface. So you can get a very good mold for your plastics. Yeah?
Due to a lot of metal and good thermal conductive? Or
No,
why?
well, this thing, where is the slide? No. Yeah, I lost the slide somewhere. It's at the end. This is for making these red knobs for safety. On the machine, you have these red alarm knobs which you push. This is a plastic. Yeah? So, but any plastic that you cast will show marks, and especially also thermal things. Because you know, if you have the same in metal casting, a thick part has got problems with shrinkage when it cools down. It's the same in the plastic. Yeah? So most plastics, they try to keep the plastic same thickness everywhere. Yeah? But if you have somewhere thicker parts, like support underneath, then you have a problem with when the plastic shrinks and it leaves some marks. So to avoid this, you should cool very close to your plastic. Yeah? So in the mold, you need your channels, cooling channels, very close to the plastic. Yeah, for a flat thing, that's easy. But for something curved like this, it's tricky. So then with 3D printing technology, SLM, you can do these. You make your mold and your cooling channels are very close to the surface. Okay, implants of different things. This is, of course, all in titanium because this is biocompatible, more or less, because it also gives some problems. Now for material performance, well, so we saw technologies. Now a little bit on the material. One of the things which is problematic, I already told you, is the direction of the layering. And if you look at specimen for the tensile tester, if your layering is like this, it will be strong. If it's like this, it will be nothing. Because here you essentially test the binding between two layers. And here you test the tensile strength of a layer. It's very different. Yeah? So you need clever thinking on the strategy of how to print so that your anisotropic properties have the correct orientation for what you want to do with it.
Depends on application.
Yeah. So you need to start thinking about your CAD model and then think about in which direction will I do the printing, or change your strategy while you're printing in the software, if you can. Make clever software for the 3D printing to get better orientation. Also, problem is, if you look at the data sheets, if you look, for example, at ABS, ABS in bulk has tensile strength of something like 45 megapascal. If you look at the wires they sell, they will tell you 30 megapascal. If you print it, strongest one will be something 20 megapascal in this direction. In this direction, you have something like 2 or 3 megapascals. So the material strength is very susceptible to your printing strategy. Yeah. Also, you use thermal technology. Means when it cools down, you have shrinkage. So you should oversize more or less your part. They say 1% approximately. Huh? Meaning if you want to have something which is 100 millimeters at the end, you need to make it 101 millimeter when you start. Yeah? This is often forgotten because you make a CAD model like you want your finished part, not your raw part. Yeah? You should think about it. Surface quality is an issue. Step size, depending on the technology. So step size is your layering size. What you also need to think about is internal cavities or the filling rate. You've seen in FDM you have these sausages of plastic. In between is hollow spots. This can be dangerous depending on what you want to do with it. I told you aerospace is one of the niche markets in which cost is no issue. Yeah? But if you want to send something in space, you better not have a cavity inside. Because this means this cavity has the pressure of 1 atmosphere. So if you go into space, your space application will explode because outside there is vacuum. So you get tremendous internal forces at that moment. Printing speed and adhesion of layers is important if you think about quality. I told you, if you print a long stretch in plastic and you return, your plastic is cooled down. Yeah? And so you have problems with this. Strength of the part, direction of printing, we'll come to some. So if you look at some of the technologies, and we see for CNC this traditional machining, speed is moderate, accuracy is very high. Yeah? Surface roughness is the best, the lowest surface roughness which you can get, and strength is the highest. Yeah? Okay, you can do whatever you want, every material more or less. Problem is you cannot color or use multiple colored. You have to treat it afterwards. And then, of course, this is something made by the guys who make 3D printing technologies. So they focus on things which is good for them. That's also why you don't find numbers here, but only like names, things like highest, lowest, but not real numbers. So I put in some other numbers to see. So if you look at stereolithography, we have tolerances 0.13, 0.15. Yeah, this is from mechanical point of view very bad. Yeah. Minimum wall thickness in SLA 5 millimeters. So for thin wall thickness, this is also not appropriate. Layer thickness is problematic. And here we see why this stepping, this is all your layers, and then you see you will not attain the perfect shape, but you will also have always have the problem, which is also the surface roughness problem, of course, and the STL with the short height. If you look at selective laser sintering, 0.1 to 0.18 tolerance, this is the same range. This is also not very good. Yeah? Wall thickness is much smaller, to 1 millimeter, that's nice. Yeah? Layer thickness to 1.001 millimeter. Yeah, but then you also need to sandblast afterwards to take out the rest. So when we look at these technologies, they're all about in this range. So dimensional tolerance, something 0.15, between 0.1 and 0.5 millimeters. This is not very accurate. Surface roughness is not mentioned here, but then you speak something in between. The best technology is maybe 20 RA, so average surface roughness 20 microns to a couple of hundreds of microns. Yeah? If you think about strategy, you also need to think about the problem of gravity. Meaning, if you want to print like this egg, yeah, you can, the egg, then you can think about your layers. You can put them all inside or all outside. So your dimensional this is especially on dimensions a problem. So you can think about, okay, maybe we make some inside, some outside. That's better. But beware, this strategy you need to be able to implement in your software for the machine. Huh? And you will also have distortion, always. Because if you print in this direction, gravity goes in that direction. So you push down on the plastics and whatever is underneath, and it will be pushed out. Yeah? So there is a lot of things to think about. Okay, the problem of surface roughness, you know surface roughness, essentially what you want to look at. From the steps you will see that you have a problem. Surface roughness in this direction is different than surface roughness in this direction. Yeah? Because of the different reasons, of course. In this direction, step size, in this direction, horizontal direction, like for instance in FDM, these sausages which are glued together. Yeah? Now, this is an interesting part and pictures. This is a part made with selective laser sintering of plastic balls. This is an SEM, so electron microscope picture. Yeah? And here we see this is the needle of your surface roughness measuring device. Tactile measuring of surface roughness. So it's a needle which go over this and then calculates your average roughness. But what happens is what you see here. You don't essentially measure the surface roughness, but you measure the force of your device because you just scratch the plastic. So if you do this wrongly with a tactile measuring device, you have a problem. So we look at it. Surface roughness made or measured with tactile measurement device, 100 microns. If you look at it optically, 500 microns. So it's not very good. Okay, yeah, this is unclear. So put together some other numbers. The velocity, so how much can you do with this for 1 hour? Yeah. And the accuracy in the end, but it's unfortunately this in inches. Now if you 3D print, there can be a lot of problems. I'm running out of time, I see, so I have to hurry up a little bit. Some of the most common problems you see here, pillowing. This is these things. This means you don't have enough layers to close. Yeah? And you don't make a hollow part, but inside you don't make it solid. You make kind of raster structure or something in it. Honeycomb structure or something, and then you print layers on top to close your part. Yeah? Pillowing means not enough layers on the top. Yeah? And then it opens up due to the thermal effect. Other things, this also happens when you're using printers. Seems there is material missing under extrusion of your material. Yeah? This is mostly a problem with the heat. This is for these plastic printers. You have to heat the wire and then print it. So heating the wire and the speed, the scan speed together, they make out the quality of your part. So it needs some clever investigation and strategy to make it okay. Yeah? It's one of the most common problems which you have. Stringing can also happen. These kind of things, which is here in between. So you should print these peaks, but when the printhead goes from this one to that one, it leaves behind some plastic materials. In this case, but in other technologies could be metal. Yeah? This is a tough one in cheap printers, because normally when you go from here to here, you have to retract your filament. Yeah? Most cheap printers cannot do this. So you will always end up with stringing. And warping. Warping is is one which often happens. Warping is what we see here. Yeah? This is all due to the thermal effect. When we print a layer, and then we return for the next layer, this layer already will have been cooled down. Yeah? So this will cool. The new layer which you print on is heated. So after printing, it will try to shrink. Yeah? Now, depending on your printing speed and the length of your paths, it will be more or less hot, the bottom layer. Yeah? The biggest problem is, of course, when the bottom layer is already very cold, you have a hot layer on top, it shrinks, and then it pulls together. You get, essentially, from a mechanical point of view, you get this when you look at the layer. You will have the bending moment, and that's the warping. Yeah? So what can you do to avoid warping? Yeah? There's these different strategies to do this. One of the things is, around your part, you first print one layer, just one line of plastic. This sticks to the plate, and then you print your part, and it will stick to this one layer. So it will be kept down. Yeah? And afterwards, you need to remove this one thing. This is one. Another thing which you can do to avoid this is print first a raster, and then print on top of the raster. So the temperature distribution is much more better. And what's the best, or one of the easy things to do if you use a printer at home, is around your part, you print a cylinder which grows with your part. So in between your part and the cylinder is some space, centimeter or something. But the thing is to avoid convection of air so that you keep the cooling down. And you also insulate your printer from the surroundings. Using a 3D plastic printer in a classroom like this would not give very good quality parts because the temperature difference is too big. Yeah? So then you need to isolate the printer from the surroundings. Because of course the plate on which you print you can heat, but the heat is lost. And the heat is only at the bottom, not on top of your part, of course. Okay, so if you look at additive manufacturing, there is advantages, of course. Design freedom, yeah? You can make any shape you want. Internal cavities and so on, all is possible, yeah? You can customize any part, and you don't need to have manufacturing skills. At least that's what they say in the flyers. I showed you that you need to think a lot about strategy on how to print, yeah, for good quality parts. Not only with plastics, but plastics is the easy one to explain, but it's the same with metals and so on. Metal printing, you also have the problem of the layering, you have the problem of the anisotropy, filling rate. You need to take care of all of this. Just a second. Okay, so you need a lot of other skills. You don't need to mill or drill or whatever, but you need to think about other strategies. So applications is almost custom or niche oriented. So some functional models, especially in metal, mostly prototype. Yeah? Prototyping is a very interesting field of working. Yeah? So that you not only have your design on the screen, but you print it out and then you can touch it, look at it from all sides, put it somewhere in to see if it's functioning or not. Yeah? And we use it for small, medium and even larger products, but not productions. So essentially for a production, for mass production, it is not a competition to traditional technologies. Not to castings, not to milling and so on, because it's far too expensive for doing this and too slow. You can 3D print a car, but if you know, like a car has got a lead time coming from the manufacturer, something like in between in the range of a couple of minutes. Meaning in a car manufacturing plant, every minute a new car comes from the conveyor belt and a new car is made. You've seen this dashboard from Ford Mondeo, 52 hours to print one dashboard. So you cannot compete with traditional manufacturing technology, only for niche. Yeah? It also came from prototypes in the past. Now we have mechanical parts which you can make in metals and so on. So the new trend is mechatronics and electronics, because you could print in sensors and so on. This is very interesting. And you also want to customize a lot. Yeah? And we see, of course, what happens. And then we see some interesting things here. Education is an important part for additive manufacturing parts. Yeah? But then we see here fit and assembly prototypes to test patterns for tooling, but for all patterns for metal casting is important. Yeah? And functional parts, okay, 30% they say, but if you look at like airspace industry, in A380, I think it's a very huge airplane. Yeah? It's probably something like 100,000 components in there. Well, 32 is 3D printed. So it's like nothing. Huh? Okay, so for interesting things is for show and tell. This is what we use in education a lot, to show things made easy now. If you want to make this traditionally, you spend a lot of time. Yeah? So this kind of mechanisms and so on, you can 3D print and show to students. For this is an interesting market. Yeah? For design, it's also interesting because you can make very interesting shapes, which is tough to make when you want to make them traditionally. And also, like this is maquettes for architects. They can 3D print your house and show you. Because if you want to buy a house, most people is very atechnical and cannot read technical drawing. But if you have a nice maquette, it's easier to show people what you're selling them. And moving objects or in and in objects. For consumer and design, it can be interesting. Yeah? Because you have the freedom of your design. Here is some examples. For prototyping, but then industrial prototypes. Once again, this one. For small series, it could be. Yeah? Now, this is a company, Materialize. It's a worldwide company. It is established from Belgium. It was a spin-off from my university. But was also interesting, these guys, they have a very big branch in Kiev. They have about 300 software engineers sitting here, devising, making the software for their 3D printing. And also for the 3D printing parts. Making the correct strategy and then adjusting it in the printing software. 300, that's quite a lot of people sitting together. Okay, metal parts for medical implants, I already told you a couple of times, but then other parts with very difficult inside structures in metal. You can 3D print them, that's nice. Nozzles and so on. Also these small parts with inside structures, and here we see this mold for this knob. Yeah? I know this very well because this was made in our campus. Biomedical, not only implants, but also this is a 3D scanned tumor, which was then 3D printed for the surgeon first to experiment on and practice before he opened up somebody's head to operate on the tumor. Huh? So also kind of prototyping thing, which is an interesting thing. It can be done in different sizes, of course. Here we see another medical implant or piece of helping not only people but also animals. And for lightweight design, it can also help because this is a metal part. This is the new metal part, but made with 3D printing. Yeah? So they saved out a lot of materials by optimizing the shape. Yeah? And then if you want to make this with traditional machining, you end up with a problem. Even with casting, this is very tough to do. Yeah, I know. Okay. And as I come from Belgium, chocolate printing is interesting to make custom-made chocolates. Okay. Nowadays, also in software, you get new tools available. This is software Creo, PTC. They have now a feature for making these inside structures easy. So the manufacturers of software also, CAD software, also put in tools now for the design and for helping you 3D printing. Okay, do it yourself, open source, but most important thing is think differently. You have more freedom now in design, but don't think that it's so easy to 3D print a good part. You also need to think about a lot. It's not like just putting it there and hoping something good will come out. Yeah? Okay, I used my time, maybe I used more than my time. But okay, that's quite okay. Any questions left? Please ask. If not, we'll end up.
Thank you.
You're welcome.